A typical kitchen refrigerator weighs about as much as two grown adults standing close together. Picture for a moment sliding that fridge across a smooth kitchen floor with a single, firm shove. Now picture a wall panel the exact same size as that refrigerator door, but light enough that a house cat could lean against it without tipping it over. That mass difference is real. It is sitting in a facility in China right now, and here is the twist that surprises even the engineers who made it. The same material that floats like cork can also sit through a direct flame test, cool off, then take a pounding rainstorm, and keep doing its job after both. By the end of this story, you are going to understand how a substance that feels closer to packing foam than to a building material can quietly carry real structural weight, and why that single shift in density may matter more to the next century of construction than almost any other material science breakthrough you will hear this year. If that surprised you, stick with me for the next 2 minutes before you click away. A quick like and subscribe genuinely helps us cover more stories like this one. And if the science behind this foam turns out to hold up the way early testing says it does, you are going to want to be following along when the next chapter drops later this season. Concrete became the default building material of the modern world for a reason that is easy to forget once it is taken for granted. It worked. 3 separate problems had to be solved at the same time, and concrete solved all 3 in a single pour from a single truck. It needed to be strong enough to hold up a building. It needed to be cheap enough that governments could afford to build entire cities out of it. And it needed to be made from raw ingredients that exist in almost every country on the planet so that no single supplier could hold the whole industry hostage. Limestone, clay, sand, water. That is the entire shopping list, and you can find it within a few hours' drive of nearly every construction site on Earth. That mix is why you can pour a footing in a village in Kenya and pour a bridge support in northern Japan using the same recipe, the same testing standards, and largely the same trained crew. The predictability alone is worth a fortune to any government trying to manage hundreds of projects at once across different provinces, different climates, and different contractors. Few inventions in human history have done more with less fanfare than this one. Now here is a number worth fixing in your head before you hear the rest of the story. Standard concrete weighs very close to 4,000 pounds for every cubic yard poured. A cubic yard is roughly the size of a washing machine. So in plain terms, a chunk of ordinary concrete the size of your washer at home weighs about as much as a small car. Imagine stacking your washing machine up against the curb and noticing that your neighbor's sedan is parked on top of it. That is the baseline. That is what every builder on the planet has been lifting, hauling, and pouring for over a century. That weight is not a footnote. It is the entire reason the next part of the story matters. The flaw hiding in concrete was never really about chemistry. It was never about the limestone, never about the cement powder, never about how the sand was graded. The flaw was weight. And weight touches almost every single cost decision in construction, starting with the first surveyor's stake driven into the dirt and ending with the demolition crew 50 years later. A heavier wall demands a deeper foundation. A deeper foundation demands more steel reinforcement. More steel reinforcement demands bigger cranes on site. Bigger cranes demand wider roads just to reach the site in the first place. Every link in that chain quietly costs more money, and every link in that chain grew heavier the moment concrete was chosen. Weight also has a darker consequence that becomes obvious the second the ground starts shaking. In earthquake country, a heavier building carries more destructive force when the earth moves under it, in roughly the same way an overloaded shopping cart does more damage to a parked car than an empty one moving at the same speed. That is not a small problem. It is the reason engineers in seismic zones pour lighter roof slabs whenever they can, and it is why so much research has gone into lightening what goes into a wall without giving up too much strength. For decades, the industry's answer to that weight problem was the kind of incremental adjustment that nobody outside the field ever noticed. Slightly lighter stone, slightly more air trapped in the mix, slightly less cement here and there. Each of those tweaks shaved off a few percentage points of mass. None of them solved the underlying assumption, and that assumption is the one worth naming out loud. The construction industry has spent over a century treating strength and density as if they were the same thing. Denser meant stronger. Hollow meant weak. That mental shortcut is so old and so baked into every standard textbook on earthworks that very few researchers even bothered to challenge it on paper until fairly recently. So when a team of material scientists in China started publishing peer-reviewed numbers in 2025 showing that strength and density could, under the right conditions, be pulled apart from each other almost entirely, the construction world had to make a choice. It could keep treating that assumption as fixed, or it could start paying attention to actual measurements instead. Before walking through how the new foam actually works, it helps to look at why earlier attempts failed in a way that very few science explainers ever bother to explain clearly. Foam-based concrete is not a new idea. Researchers in multiple countries tried it across many decades, and the same problem tripped up almost every version of it. The bubbles did not behave. Some stayed huge, some collapsed flat. The internal structure ended up looking like a chunk of pumice stone someone had stepped on, full of random cavities of wildly different sizes, with no rhyme or reason to how they were arranged. Stress piled up at the weak spots between the bubbles, cracked the material open, and turned what should have been a structural wall into something closer to a stack of stale crackers. The shape problem stayed unsolved for generations. And here is the breakthrough worth dwelling on for a moment, because this is where the everyday comparison earns its keep. Think about a tray of ice cubes pulled fresh out of a freezer. The cubes look the same. They sit at the same height. The gaps between them are consistent. Now think about a tray of crushed ice dumped out of a bag at a fish market. The pieces are different sizes. Some are large, some are powder. The pile has random gaps everywhere. If you stacked a wall out of uniform ice cubes, the wall would behave predictably. Stack the same wall out of crushed ice, and you would not trust it to hold up a window. What the Chinese research team managed to do was invent a way to control the bubble before it ever set, in roughly the same way a good ice cube tray controls the size of every cube inside it. Nanoscale surface treatments are mixed into the foaming agent so the bubbles rise, hold their shape, freeze in place, and cure into a uniform internal lattice with predictable air pockets throughout the entire body. The result is a foam capable of densities as low as roughly 100 to 200 kilograms for every cubic meter, which is a small fraction of what standard concrete weighs, sitting somewhere around 2,400 kilograms for the same volume. In other words, you can hold a sample of this foam in one hand. The same volume of ordinary concrete would demand a small forklift. Here is the deeper point hiding inside that math. When every bubble is roughly the same size and evenly distributed, stress does not stack up at random weak points anymore. It spreads out across the entire body of the material in a balanced way, almost the way a six-legged picnic table feels steady on uneven ground while a three-legged stool wobbles on a perfectly flat floor. Uniform pores are the entire reason the new version holds its shape under real load, while the older versions cracked under far less. The chemistry behind why the bubbles hold their shape is worth a closer look, because the trick is genuinely subtle. Normal foaming agents used in older, lightweight concrete rely on a thin film of detergent like soap to keep each bubble inflated. That film is fragile. It leaks air, it pops under vibration, and it reacts with the alkaline cement paste in unpredictable ways that change from one batch to the next. The new treatment adds a nanoscale particle layer to the bubble wall, a coating so thin that millions of them could sit side by side on the tip of a pencil, but strong enough to act like a second skin wrapped around each bubble. Once that skin is in place, the bubble behaves less like a soap film waiting to pop and more like a tiny balloon with a rubber membrane. Pressure that would have burst the old version just gets absorbed by the new flexible coating. The result is a foam that survives the trip from the mixing drum to the wall cavity, survives the vibration of being pumped up several stories high, and survives the curing heat that hardens the cement around it without collapsing. That single shift in chemistry is the entire reason the field results started looking different from anything that came before. It is also worth knowing that this idea is not the first time the industry has tried to lighten walls with trapped air. More than a century ago, in 1923, a Swedish architect named Johan Axel Eriksson patented a process for making what we now call autoclaved aerated concrete, where cement slurry is mixed with a foaming agent, poured into big blocks, and then set under high-pressure steam in an industrial oven. Aerated concrete walls can still be found in apartment buildings all over Europe and East Asia today, and millions of families live inside them without ever stopping to think that their walls are mostly air. The reason aerated concrete never replaced solid concrete everywhere is that autoclaving requires factory-scale equipment. The blocks are heavy enough to still demand a small forklift on site, and the recipe is rigid enough that field adjustments are nearly impossible. The new Chinese foam keeps the original insight, air-filled walls done right, but solves the field deployment problem by removing the autoclave altogether. That is, the through line connecting two technologies 100 years apart, and a fairly elegant one. Now comes the part of the story where honesty matters more than enthusiasm. Foam at the very lowest densities has a compressive strength well below what standard structural concrete is rated for. We are talking single-digit megapascals compared to the tens of megapascals most structural columns and beams are engineered to carry. That is a real gap. It is not a marketing exaggeration, and it is not something to brush past. For load-bearing columns, primary structural beams, or any element where the entire weight of a multi-story building sits on a single piece, this foam is not the right tool on its own. Where it does shine, and where the technology actually has a clear path to widespread use, is in the vast majority of wall systems where full structural strength was overkill in the first place. Interior partition walls, insulation panels wrapped around older buildings, roof decks where weight, not raw strength, is the limiting factor. Disaster response shelters where speed of deployment matters more than how much load the walls can carry for decades. None of those applications demand the multi-decade compressive performance of structural concrete. So the strength gap that sounds alarming at first glance turns out to barely matter for the actual jobs this material is suited to take on first. And that is not the only advantage hiding inside the same air pockets that drop the density. Those same trapped bubbles do something else that concrete has never been able to do at the same time. They hold heat. The insulation performance of this foam runs several times better than a standard concrete wall of the same thickness, in the same way a down jacket keeps a person warmer than a leather jacket of the same weight. That means a builder can meet modern energy codes without stacking a separate insulation board on top of a concrete wall and paying for both layers. One material does both jobs. That alone is enough to make builders stop and take notice, because wall assemblies have been a hidden cost driver for as long as anyone reading this has been alive. Then there is the use case that almost no one thinks about until a flood or earthquake forces it onto the news. A panel this light can be carried into a cut-off village by hand, hauled up a mountain road by a small truck, or lowered from a helicopter into a zone where the roads are gone and the cranes are still buried in mud. After an earthquake in a remote province, after a landslide has blocked the valley road, after a river has wiped out the only bridge, the speed at which shelter reaches people is measured in lives. A material that removes the heavy lift bottleneck from disaster logistics is not a luxury item. It is one of the more meaningful humanitarian upgrades the construction industry has seen in a generation. To put real numbers on what that actually looks like in practice, picture a single medium-lift helicopter with a useful payload capacity of around 2,000 kilograms. With standard concrete wall panels, that helicopter could deliver enough wall material to build perhaps 2 family-sized shelters before having to fly back for more. With foam panels at the densities measured in the Henan pilot, the same helicopter could carry enough wall material for 16 or more family-sized shelters in a single sortie, because each individual panel weighs a small fraction of its solid concrete counterpart. That is an order of magnitude difference in how fast emergency housing can reach a cut-off valley, and it is the kind of math that a relief logistics officer notices the first time they see it on a planning sheet. Now for the receipts, because a story like this only matters if the numbers and the dates can be checked by anyone willing to spend an afternoon looking them up. Field trials have moved out of academic journals and into real construction sites in Henan and Jiangsu provinces, beginning with peer-reviewed laboratory work in 2025 and rolling into wider commercial production in 2026. Manufacturers are now producing the nano-modified foaming agents at industrial scale and feeding them directly into concrete mixing equipment already installed at hundreds of existing plants across China. Crucially, no entirely new factory had to be built from scratch. The switching cost for an established concrete plant was the price of a new additive, not the price of a new production line, and that single detail is what made rapid adoption even theoretically possible across a country with thousands of active plants. To put real numbers on what those field trials actually delivered, the first verified pilot project, an agricultural village retrofit program running through Henan province during the spring of 2026, replaced roughly 900 interior and exterior partition walls in 46 single-story rural homes. The wall panels were poured on site using the new foam formulation at a target density of 160 kilograms per cubic meter, weighed about 1/5 of the standard concrete panels they replaced, and recorded thermal resistance values roughly 3.5 times higher than the original masonry walls under independent third-party measurement. The crews that poured the panels had no prior foam concrete experience and completed the program inside a 6-week training window before the first wall went up, which is itself a quiet vote of confidence in how simple the new system is to adopt on the ground. A second pilot, run through a state-backed retrofit program in parts of Jiangsu province through 2025 and into early 2026, focused on older apartment blocks built in the 1980s with essentially no insulation value in their exterior walls. The crews removed the outer rendering, sprayed a layer of the foam directly onto the existing brick substrate using portable mixing equipment that fits in the back of a small truck, and brought the wall assembly up to current National Thermal Code without changing the footprint of the building or the size of the windows. The retrofit cut heating energy demand for those apartments by an independently measured margin in the range of 40%, and the building managers reported no cracking or surface flaking after the first full winter and summer cycle. The scale of what those two pilots represent is worth dwelling on for a second. If even a small percentage of old masonry buildings across China, much less across the rest of the world, treated exterior walls this way over the next decade, the cumulative energy savings would dwarf any single retrofit program and would not require a single new construction site to be broken ground. Public testing data filed with Chinese national building materials standards bodies now lets independent engineers verify the density claims, the strength claims, and the insulation claims directly against an open benchmark, rather than trusting the manufacturer's own brochure. That kind of transparency is what turns a clever laboratory result into something engineers on the other side of the planet will actually risk building with inside a real project, because nobody wants to be the contractor on the first building that fails under a winter storm. The international response has been quick, in the way the construction industry is quick, meaning not very quick at all in human terms, but lightning fast by the standards of how slowly building products are usually adopted. Multiple international patent families covering variations of nano-stabilized foam concrete chemistry have been filed not just in China, but also in the United States, Germany, and South Korea over roughly the last 3 years. Construction material suppliers in Henan have already moved well past sample batches and are running mass production for the stabilizing foaming agents themselves. European insulation manufacturers have begun evaluating the material for retrofit markets, where tightening energy efficiency mandates on the continent are forcing developers to rethink how walls are assembled. The math working in favor of adoption is straightforward enough that it deserves to be spelled out. A typical exterior wall assembly in new residential construction today uses a standard concrete block layer on the outside, a separate insulation board in the middle, and an interior drywall finish on the inside. That 3-layer sandwich has been the default for 30 years and works well, but it carries the cost of 3 separate materials, 3 separate trades on site, and 3 separate waste streams at the end of the building's life. A foam wall assembly built around the new material collapses 2 of those layers into one. The foam panel acts as both the structural exterior skin and the insulation layer at the same time, leaving only the interior drywall finish to be added separately. Independent cost studies done across comparable projects in eastern China during 2025 put the per square meter installed cost of the foam assembly at roughly 15 to 20% below a traditional 3-layer wall once labor and waste handling are factored in, and the gap widens further at higher density grades where cement content savings dominate the bill. That cost gap is precisely the kind of arithmetic that turns a science story into a procurement story, and once procurement teams start paying attention, the rest of the industry follows, whether or not the original researchers ever intended it to. So the double win that builders keep coming back to is simple. Cut cement content by roughly 1/3 per wall, cut wall weight by a similar margin, keep the insulation performance that codes now demand. That is a combination of 2 pressures hitting the same brick wall at the same time, and no serious procurement officer can ignore it for very long, especially as material costs climb faster than labor costs across most of the developed world. It is worth zooming out for a moment and asking what all of this means beyond any single project or any single province. Cement production, just for the cement portion of concrete and nothing else, is commonly cited at roughly 8% of global carbon emissions, which puts the cement industry in a range frequently compared to the entire global aviation sector combined. That is a piece of the climate picture that is rarely mentioned alongside cars and planes, but it is sitting right there in the same basket. Every building constructed out of foam-based wall panels instead of solid concrete shifts a small slice of that number downward, and because the construction industry operates at a genuinely civilizational scale, with roughly 4 billion tons of cement poured worldwide every single year, even partial adoption adds up across decades in ways no single project ever could on its own. The compounding effect lives in the math of how many walls get poured between now and the middle of the century, and how many of those walls quietly carry a different recipe than the ones being poured today. And it is not just the developed world that should be paying attention. The places that have historically had the hardest time getting traditional concrete delivered in the first place, rural provinces in Southeast Asia, mountain villages in sub-Saharan Africa, fast-growing peri-urban settlements across South America, were the places where weight, transport distance, and on-site equipment constraints always hit hardest. A wall panel that two people can carry changes the math of what gets built and where in those regions in ways that almost no other single technology has done in the last 50 years. That is the macro picture, and it matters because it explains why governments, not just builders, are paying attention. So what could go wrong, and where is the weakest link in this whole story? Because it would be dishonest to pretend there are not several, and a fair account of any new technology has to name the obstacles out loud. Production capacity for the specialized foaming agents is still concentrated in a small number of Chinese manufacturers today, which means global supply could bottleneck fast if international demand spikes faster than existing factories can realistically scale up. Building codes in most countries, including large parts of the United States and the European Union, have not yet been updated to formally certify this kind of foam as a structural or even semi-structural material, and certification work has historically taken several years, not months, to complete properly through every regulatory body involved. In the European Union specifically, the revised Energy Performance of Buildings Directive now mandates whole-life carbon reporting for new construction beginning in 2030, which is exactly the kind of regulatory pressure that pushes developers toward lower carbon wall systems, but the certification clock still has to finish before the foam can carry the structural stamp on the blueprints. Long-term durability data beyond a handful of years of real field exposure simply does not exist yet, because the material itself is genuinely that new to the global market, and freeze-thaw cycles over decades can stress a wall in ways no accelerated laboratory test can fully replicate. Cost parity with traditional concrete has not been proven at every density tier, particularly at the ultra-low end, where manufacturing precision drives production price upward noticeably, and where the marginal buyer still picks the cheaper option regardless of insulation savings. And workforce training gaps remain real too. That last point deserves its own breath. Many construction crews around the world have spent their entire careers working with concrete, brick, and mortar. They have never seen foam pumped through a hose. They have never judged the consistency of a pour by feel the way the new process requires. Even the simplest sounding change, spraying foam onto an existing wall, has a learning curve that only shrinks after a few hundred square meters of real practice. Retraining an existing construction trade is not a single training session. It is a multi-year migration where the most experienced workers teach the newer ones, while the production side of the industry quietly expands the supply chain in parallel. That timeline is not fast, and it is not free, and pretending otherwise would be selling a story that the people doing the actual work on real job sites would spot immediately. None of those obstacles are secret, and none of them are being hidden from regulators or investors. None of them change what the laboratory science clearly shows is achievable. They define the gap between what is technically possible and what will actually be built at scale within the next decade. Closing that gap is an investment problem, a policy problem, and a coordination problem as much as a manufacturing one, and it is worth being honest about that gap rather than pretending a new foam in a research paper is going to rewrite the global construction industry on its own by next quarter. Here is the part of the story worth carrying forward before the chapter closes. A team of researchers has shown, with open and checkable data, that strength and density no longer have to travel together inside a wall. A wall that used to weigh as much as a small car can now weigh as little as a house cat, hold real structural load for the applications it is suited to, insulate at several times the performance of the old material, cut carbon emissions built into the wall itself by roughly a third, and arrive at a remote job site carried by two people instead of delivered on the back of a flatbed truck. That is not incremental. That is a different category of solution than the construction industry has had on the table for the last 100 years, and the rest of the industry is already moving to keep up. And because concrete-based construction operates at a truly massive scale, with billions of tons poured every single year across every inhabited continent, even a partial shift toward this material compounds over decades in ways no single building ever could on its own. If you are new to the channel and stories like this keep changing how you think about the materials quietly holding up the world around you, a thumbs up genuinely helps us reach more curious listeners, and subscribing with notifications turned on is the simplest way to make sure you do not miss the next breakdown. We publish new long-form deep dives exactly like this one every single week, and the next one is going to tackle an even stranger idea you may have already heard whispers about: concrete that fixes its own cracks without anyone calling a repair crew. If you are curious about that one, you will not want to miss it. Now, I genuinely want to hear from you in the comments below. If someone you love needed a new wall built tomorrow, would you feel safe trusting a material this light to do the job? Or does the raw density of old-fashioned concrete still feel like the safer bet to you personally?